Alright, like I said, we are live a little bit early. I'm going to go ahead and get started so we don't eat up into the next time period. Alright, current in a series LC circuit. Lags the voltage by 90 degrees. So this is LC, that's inductive and capacitive. So current in a series LC circuit has no resistance. Well, it's series. Okay. Excuse me. Alright, current in a series LC circuit is the same. It's series. That's the operative word. I was trying to think, like, well, you need more information. A circuit is considered to be resonant when XL equals XC. I think we touched on that on the very last question of the last video. Resonance is when very simply put, resonance is when XL equals XC. You can get to resonance by adjusting the frequency on a circuit, and that will give you just the, like, you can get just right with the resonance and completely eliminate your reactive power. It's not practical usually. It's usually very specialized circuits that this happens in. If a series LC circuit has an XL of 10 ohms and an XC of 10 ohms, and the frequency is increased from 60 hertz to 100 hertz, the circuit will become blank. So it's series. Let's open up. I don't know why I keep closing paint. I need paint. Hang on, let me move my coaster. I had to move my drink to move some other things. There. Alright. So X of L equals 2 pi FL. So if F goes up, X of L goes up. X of C equals 1 over 2 pi FC. So if F goes up, X of C goes down. So in a circuit that contains both of them, if you increase frequency, X of L will go up and X of C will go down. And this is series. So in a series circuit, the amount of power consumed by a device in every circuit, the amount of power consumed by a device determines whether it's inductive or capacitive. In series, the higher the X of L, or whichever number is higher in series, is going to consume more power, which will make it more of that. So this will become more inductive. If it was parallel, though, remember what we were talking about earlier with a parallel circuit, the lower a leg drops, the more current and the more power is going to go through that leg. Just like lanes at the checkout, the less resistance there is in the lane, the more people go through that lane, and the less people go through the slow lanes. So in parallel, it's exactly the opposite of that, and the thing with the lowest resistance is going to make the current more of that thing. Alright, if a parallel LC circuit has an XL of 10 ohms and XC of 10, okay, this is what I just said. It's the opposite question. So whenever you get to the test, make sure you keep that straight. Parallel, the higher resistance, or the higher ohm value, is what it is. In parallel, did I say parallel twice? In series, like this one, it turns inductive whenever you increase the frequency. In parallel, it turns capacitive when you increase the frequency. Just make sure you pay attention and read your questions. Number 5, a blank is in an LC circuit will cause an increase in the capacitive reactance. So to increase, a decrease in the inductive reactance, they don't directly connect to each other, so B isn't real. And D isn't right. So a decrease in the frequency, let's look at our formula. So X of C will do the opposite of anything down here. So if F goes down, X of C will go up. And that is A. So A is the answer here. Alright, what is the applied voltage for the circuit in the figure below? Oh, given X of L is 100 and X of C is 52. Well, since they're in series, you can just subtract them from each other. Z is going to be, what, 48? So if you're able to find Z is equal to 48, and this is just, Z is normally the square root of R squared plus XL minus XC squared. But if you don't have R, then you're just getting the square root of XL minus, and this is parentheses, XC squared, which these squares cancel out, so Z is equal to XL minus XC. And that's the absolute value, because you can't have a negative resistance. Anyway, that was 48 ohms. I total was, I believe, 5 amps. And E total was it 5 amps? Yes. Uh, 48 times 5, 240. 240 volts. And that's it. All you got to do. 240 volts. We got an explanation. Well, they did it backwards. So each component, it's series. They both have the same current. They found the voltage of each device, and then subtracted those voltages from each other, giving the same answer, but in a different way. It's interesting. The correct vector relationship between voltage and current in a series LC circuit. Series? Well, in series, current is at 0 degrees. So it's not A or B. Voltage leads current, and inductive voltage leads current, and current leads capacitive voltage. So it is C. Alright. Next. What is the total reactance in a series circuit with an inductive reactance of 15 ohms and a capacitive reactance of 5 ohms? They just subtract from each other. 10 ohms. Right there. Well, I started this early, but it's The questions have been very simple. What is the impedance of a series circuit with an inductive reactance of 15 ohms and a capacitive reactance of 5 ohms and a resistance of 10 ohms? Okay. So starting with the same numbers as the last question, you end up with a triangle. So this is a series circuit. Once you've subtracted your inductive and capacitive reactance from here, you have a triangle with R equals 10 ohms and X of L minus C equals 10 ohms. So square root of 10 squared plus 10 squared is 10 squared is 100. Square root of 200 is, I don't know, like 140. Oh, 14.1. Had too many zeros. Uh, 14 is close enough to the answer for me. So, series circuit still. I keep getting a buzzing in my headphones. I'm not sure what it is. It might be that there's thunder outside and my headphones are picking it up somehow, but that would be weird. That'd be like, thunder's about to hit my house. Alright, identify vector B shown for the impedance triangle. So vector B in an impedance triangle is going to be X of C. Done. Vector B is X of C. For impedance, vector D in an impedance triangle is going to be Z. That's the impedance. That's the actual impedance. Uh, 12. We got 13. Alright, what is the current flow through the inductor in the figure below? Ooh. Let's see what they gave us. I total is 4 amps. So we know there's 4 amps through R1. Z of RL. ZRL is 28 ohms. We will come back. Oh, there's no capacitor. Okay, I can work with that. Current flow through the inductor. R1 is 40 ohms, R2 is 40 ohms, X of L is 40 ohms. Oh, it's... Okay. We'll work this step by step. Is this the same circuit? No, it's different. Okay. But let's open up our picture. Looking through. This is probably the most complex. Oh, damn it! Probably the most complex circuit that is going to be presented. Let's do 2 times. Yeah, that's perfect. So we have Z. This is a combination circuit. Z, we have R1, R2, X of L, and then Z of L and R2. And this will be down there. Okay, we have I total, I of R1, I of R2, I of L, which is I of L is our goal. I of L dash R2. Then we have E total, E of R1, E of R2, E. I didn't mean to make all these green. My bad. E of L and E of L dash R2. Okay. So let's get our numbers back. I total is 4. ZRL is 28 ohms. I total is 4 amps. You know what, let's make our numbers red. 4 amps. And if you look, when you I can't point. Don't point at the screen, John. When you combine these two when you combine those two, they'll become a single series resistor. And that will make this whole thing in series. R1 will have, get a pencil, 4 amps, and I of L dash R2 is 4 amps. Okay. So let's go back, get some more numbers. I think Z was 28 ohms. Okay, I see some things forming. R1 is 40, everything's 40. So this is all 40 ohms, 40 ohms, and 40 ohms. Okay. Some people are saying the stream is lagging real bad. I'm showing an excellent connection, so I don't think it's on my end. So we'll see what happens later. I might have to re-record this if it's bad. Okay, so let's take any rows we have and multiply them across. Close my calculator like a dummy. Okay, so let's start from the top. We don't have a Z, so that's not worth it. 40 times 4, 160. 160 volts. And then 28 times 4 is 112 volts. Okay. So that tells us the voltage that's on these legs. And in parallel, since the voltage stays the same, we can move, just like when we were doing combination circuits, we can move this 112 volts up here. Alright, so now we can 112 divided by 40, 2.8 amps. And then I'm going to do, well, that's also going to be 2.8 amps. Let's see what happens if we do, because these two amperages are in parallel, and they should combine. You should have 2.8 amps and 2.8 amps. Now I drew this triangle upside down. My bad. You should be able to do Pythagorean theorem. Let's see. 2.8 and get 4 amps. Squared plus 2.8 squared, close it, square root 3.959. I'm gonna call that close enough. Okay, so now (2.8), which is what I found. Yep, 2.8. Good. All right, and there is a explanation which shows ERL is 112. 112 divided by 4. So yeah, they just went right there. They didn't do the full chart and find all the things. And I'm just, whenever I do things like that, I'm just showing that, like, if you make the chart and just fill out the things that you know, you'll eventually get there. All right, what is the impedance for the parallel RL branch? That's this. In the figure below, assume a voltage of 120 volts across the parallel branch. Given R1 is 30, R2 is 30, X of L is 30. Wow. That's a nasty question. Okay. So, right off the top, well, right off the top, you know the resistance R total is less than 30. But, so let's go back to, I'm going to delete a bunch of stuff. So what they're telling you to do is assume a voltage of 120 volts across the parallel branch. So what that means is you don't know what X of L, what the voltage, like they didn't give you enough information to solve this. But they told you just use 120 volts across those two. That's it. Use 120 volts. And I think they said 30 ohms and 30 ohms. That's it. Yeah, 30 ohms. So this is what you're working with. Easiest thing to do is kind of what I did at the very last step there. 120 divided by 30 is 4 amps and 4 amps. So 4 amps and 4 amps. Now you just plug it in your calculator. It's Pythagorean theorem. Open parentheses. That's clear. Open parentheses. 4 squared plus 4 squared. Close parentheses. Square root of that. 5.66. And since voltage stays the same, you have 120 volts. Now it's just simply 120 divided by 5.66. 21.2. 21 is the answer. And that finishes our day. Good job, guys. Don't forget to, take your time on your test, read all the questions, make sure you're doing a good job. All right, guys. I will see you guys. Or I'm going to put up a new quiz in a moment. Well, I'll put it up right now. Why not? The new quiz is just everything we've done today. So second year, AC Theory, AC Theory 2, AC Theory all lessons. Give you more than one attempt. Alright, so I mean, this isn't like the last quiz. This is just a 40, should be 41 question quiz. I didn't remove that very first question from the day. Alright, have fun with that. I'm going to end this stream here.